Hi, everyone. I'm Kyle Beauchamp. I'm a research fellow at Memorial Sloan-Kettering Cancer Center. And today I want to tell you about our work building Python tools for biophysical simulation. And to begin, I just want to point out that we've all benefited handsomely from Moore's law, which has essentially doubled the transistor counts of microprocessors consistently since the 70s. And so we've seen really transformative improvements in computing performance over the years. And this is a major benefit for data science, and it makes one wonder, is there a similar trend in medicine or health? And you might ask, well, is it easier to develop drugs these days? Is it cheaper to develop drugs? And I'm afraid to tell you that the answer is a resounding no. If we look at the number of new drug approvals from the 1940s to the present, we see that really it's been essentially constant over the years with a few blips here and there, but overall there's no long-term trend for greater efficiency or more drug approvals over time. You could ask a similar question and look at how much it costs to develop a drug. And here, people have pointed out, industry commentators, for example, have pointed out essentially a reverse Moore's law, where over time it's become increasingly expensive to develop drugs and cure diseases. So in 1950, $1 billion could essentially develop about 50 drugs. So that much capital investment could bring 50 drugs to market. And today, that same $1 billion will not even bring a single drug to market. So if you're like me, you'll find this pretty alarming and quite scary. And so, in fact, if you look at today's drug discovery opportunities, it costs $2 billion to develop a drug. It takes 15 years, and it fails essentially 95% of the time. So this is unfortunate because we don't really have any better alternatives. And some people have even pointed out that if this trend continues, it will no longer be profitable to cure diseases. And so there will be no investment and no one will do it anymore. What I want to talk about today is whether computers can help us to design drugs in a more perhaps futuristic way. So before I begin, I need to give you just a very brief introduction to some of the science behind what we're doing. And so I want to introduce some basic concepts from biophysics. So this is a cell. It could be a human cell, a bacteria, what have you. I'm just looking at an artist's rendition. And the key point is that this cell is a bag of protein machines. And so you see the blue blobs, the yellow blobs, the orange blobs. The blobs are just machines. They do things. And when they do things incorrectly, that leads to disease. And so how drugs work is that a drug typically, such as the one shown here in purple, a drug will bind a protein and essentially help it do its job properly or prevent it from doing its job improperly. So here I'm looking at a drug binding to what's called Src kinase, and this is a protein that's implicated in human cancer, and essentially it tells cells when to grow and when not to grow. And obviously if you're growing too quickly, then that's a problem. So this is basically the premise behind a lot of the things we're doing here, where you have a protein, you want to hit it with a drug so that you can basically tell the protein to behave properly. So this leads us to a few questions in these challenges in molecular medicine. Can we link this nanoscale biophysics with human disease? And can we use this knowledge to engineer drugs that bind proteins and achieve some sort of therapeutic action? And so what I want you to notice is that both of these challenges here are challenges that happen at the nanoscale, at the length scale of atoms and molecules and proteins. And so that's the length scale at which we want to do use computation to approach these problems. So the technology behind everything I'm talking about today is a computer simulation technique known as molecular dynamics, where we used physics-based simulations of biomolecules And it's going to look something like this, where we're going to essentially use the same physics you learned in college to simulate a protein, such as the one shown here in white, and simulate a drug, perhaps a drug binding to the protein. And so this movie comes from researchers in New York City, actually, at D.E. Shaw Research. But the key idea is that we're going to try and simulate the physics of these nanoscale machines and use it to design drugs that help them do their jobs better. So today I want to talk to you more about the software behind what we're doing. And so what I haven't told you yet is that the kinds of simulations that I've talked about are extremely challenging computationally. And so the protein that I showed you, if you want to simulate that protein in a bath of water, which is where it naturally will live, is basically we're looking at a system with 10 to the 5 atoms, hundreds of thousands of atoms. And what's even worse is that we're interested in simulating biologically or medically relevant processes. And so these processes occur on the second time scale, the millisecond time scale, or the microsecond time scale. But because of hard physical constraints in how we run these simulations, we have to simulate things essentially 1 femtosecond at a time. And so we're talking about spanning essentially perhaps 15 orders of magnitude using computers, and that we need to repeat an iteration of our simulation almost 10 to the 15 times. So obviously this is a grand computational challenge, and what we've developed is a library called OpenMM, and this is work from colleagues at Stanford, led by Peter Eastman and Vijay Pandey, and others, but we have developed a GPU-accelerated molecular dynamics library that is a C++ library with Python bindings, and actually a number of other bindings. But we provide hardware backends for CUDA, OpenCL, and CPU platforms, and the end result is that we can simulate with a modern GPU essentially 100 nanoseconds per day. And that's 10 to the minus 7 seconds. And so that brings us about halfway to the timescales that I was telling you that we needed to reach to actually make an impact in disease. So we went from 10 to the minus 15 seconds to 10 to the minus 7 seconds, and we're still a long ways away. And so another technology is that we are deploying this GPU-accelerated dynamics engine on Folding at Home, which is the world's largest distributed computing project. And so with Folding at Home, we have access to hundreds of thousands of CPUs, tens of thousands of GPUs, and essentially 40 petaflops of peak performance. And so we are simulating hundreds of microseconds per day now using this resource and the donors that provide access to their GPUs. And because of this, many people have published a number of research papers in biophysics based on results from this supercomputer. So what you might wonder is what kind of, are there any data challenges associated with generating this huge amount of data? The answer is yes. And so more colleagues at Stanford, led by Robert McGibbon, have developed a library for doing trajectory I/O on the output of these simulations. And so there's a library that we've developed called MDTraj, which is a Python library for reading and writing the trajectory objects, or essentially the movies that come out from these simulations. And so we read a wide number of formats, and we can perform arbitrary geometric analyses, calculating things like distances, angles, root mean square deviations. And these calculations are kind of the standard bread and butter ways that people look at protein structure and dynamics. Furthermore, we've optimized our code using NumPy and SSE where appropriate to really scale things up to the full, level necessary to analyze Folding at Home data sets. So, for example, this is just an example of the Pythonic API. You import the library, you load a trajectory object. What you get back is just a trajectory object, and then you call some analysis function on that object. And here I'm plotting essentially a time trace of some geometric quantity during the course of the movie, or the trajectory object that you get back. And so We've also built this into the IPython notebook so that we can visualize the three-dimensional structures of proteins as a function of time. And so I'm not going to go into a full tutorial today, but I'm just going to say that we have a IPython notebook widget that uses WebGL and a viewer for proteins, and you can actually use that to kind of to watch proteins wiggle in your trajectory data. So another challenge that we face is that it's not enough to just generate a movie and calculate some structural property. We really need to find meaning in these massive simulation data sets. And finding meaning, it's essentially the same sort of challenge that data scientists face in a number of disciplines. And so we have developed a set of tools called MSM Builder and Mixtape. And these tools allow us to essentially build machine learning models to understand the dynamics of proteins from our simulation data. To put this in a little better perspective, here is an example of an output model from our software pipeline. The idea is that we want to understand how a protein changes shape over time. And to do this, we're going to build a network model of the protein. So here we're looking at how the protein goes from an unfolded state to a well-structured folded state. And we build what's called a Markov state model. It's similar to a hidden Markov model, which many of you have probably used as a standard routine tool in data science. But the idea is that the protein is wiggling and jiggling, and you treat that process as a jumping process between discrete states, or essentially a network-like model. So with this capability, we're currently in the process of developing our next generation of this software. And one of the key ideas that we're pushing is tighter integration with the wider Python data science community. And what we mean by this is that our next release, which we're codenaming the next release Mixtape right now, but it's just a code name for the third release of MSM Builder. But what we're really pushing for is something that's sklearn compatible so that we can plug and play with kind of the industry standard machine learning tools that are available to people. And so just to give you a feel for what this means, we import a bunch of modules, we fetch our data from the cloud, we generate a list of trajectory objects from the data set, we instantiate a few objects, and we plug them together into a pipeline, which is a standard way of working with sklearn, is you pipeline different models together, and then you fit that pipelined model onto your data, which in our case is a set of trajectories. But this pipeline sort of mentality is basically a key component of how sklearn works, and we're trying to make our tools kind of plug and play compatible. So to change gears a little bit, I also want to talk about some of the work going on at Memorial Sloan-Kettering. And we are currently developing a tool called Yank, which is a tool for fast calculations of binding affinity of drugs and proteins. And it's fast because we're essentially using some tricks from statistical mechanics where we're essentially letting the drug, which is the yellow molecule, we're letting it vanish. And so it basically becomes invisible to the protein. It turns out that this is a very clever and efficient way to estimate the binding affinity, or how tightly this drug binds a protein. And so by using tricks like this, we can dramatically accelerate how quickly we can calculate binding affinities. And so this is the basis for this software package that we're currently en route to have a release in the near future. I want to change gears one more time and talk a little bit about the difficulties in developing and releasing scientific software in Python. And so feel free to interrupt me if people want have questions. But a few weeks ago, I had a user come to me, and he told me that, oh, I couldn't install your module. Like, he said, oh, I just couldn't figure it out. I used easy install, and it just didn't work for me. And, well, I thought easy install worked, but obviously it didn't work for him. And this is actually a pretty common sort of thing in scientific computing, in that people have difficulty getting the whole pipeline up and running, getting the whole stack up and running. And I actually probably get some sort of issue like this maybe once every 2 months or something, depending on which library we're talking about. But and if I look back to my own history, when I started my PhD in 2008, I had to build basically everything from source. I had to build NumPy, SciPy, and it was a major challenge. And so here I'm showing you a graph of the dependencies of our various software packages. Yank and OpenMM are on the right, and obviously they all depend on NumPy and SciPy. The nodes that are red are things that I consider hard to build if you have to do it from scratch. And so basically in 2008, everything was hard. Eventually, things like nthought Python came around, and things got a little bit easier in that it was easy to get NumPy and SciPy up and running. And so it became easy to get NumPy, SciPy, NetCDF, but there were still a few things that are still pretty challenging. So things like CUDA, CBake, they generally had pretty strong version dependencies and were just not always pleasant to get up and running. I'm going to tell you shortly, but today I think we're pretty close to having things almost fully automated in that we're using conda to deploy pretty much everything, and it's becoming a much more pleasant experience getting things up and running. And so one of the potential pitfalls that a lot of people run into is what's known as glibc hell, where you build your libraries on a modern computer and then you want to send them off to your friend who has a sysadmin who insists on using an ancient version of Linux, and they can't use the libraries that you built, but you don't want to downgrade your system to make something that works on his system. It turns out we've pretty much solved the problem now by picking a sweet spot of CentOS 6.6, where we provision a vagrant virtual machine and build all of our recipes on CentOS 6.6. And we've got this kind of automated, and we have the virtual machine on GitHub now, or at least the provisioning script. And so we've basically automated the process of making making libraries that run on pretty much all the hardware that we've come in, or hardware and software that we've come into contact with. And I am happy to say that by using this pipeline, the same user that came to me complaining is actually up and running now just by using a conda-based install. So I think we're making progress in getting things into users' hands so that scientists can do the science and not focus on building libraries all day. So, and what's more is that now we are in progress, we are developing a meta package for installing our entire suite of computational tools. So the entire suite for simulation, data munging, model building, visualization. We want to be able to install all of these tools with a one-liner, and I actually have a alpha version of that one-liner up and running. We're probably another few weeks from having an actual full-fledged beta release, but a lot of the work is done, and so it's actually, this sort of thing works where you can install the entire suite of software tools with a one-liner. Dependencies are handled automatically, and so it seems to be a pretty reasonable sort of approach. I want to change gears one last time and talk about how we might use these models and falsify them in the wet lab. So I've told you about a lot of computational models, but models are really useless if you have no way to validate them, to falsify them, or refine them. And this sort of validation occurs by making real measurements in the wet lab, but that's really expensive. So chemistry, biology, and biophysics, they're really labor-intensive things to do. And we're talking about models with thousands of parameters, which means you probably need to be making thousands of measurements. So we have a really massive challenge with reproducibility and scalability. So work in the CUDA lab, and this is work from Jan-Henrik Prinz, Bas Rustenberg, Sonja Hansen. They've been developing software libraries to make experiments as easy as programming in Python. So the idea is that you can import some modules, you can instantiate some classes, and kind of string them together to actually perform experiments in the wet lab. And these experiments are going to be performed on a robot that looks something like this. But this is actually building the robot that we have at Memorial Sloan-Kettering. What? No, they're just fast forwarded. I cannot. All right, so yeah, that's basically the robot that we're using. And let's see, sorry about the volume, but it was my poor little MacBook Air speakers. But just to leave you, I just want to give you our vision for what biophysical modeling and experiment should be, and that we really want it to be reproducible, automated, testable, and really just useful for making predictions and testing them. And with that, I just want to thank all the people who did the work. My boss, John Cadera, collaborators at Stanford, particularly Robert McGibbon, Peter Eastman, Vijay Pandey, collaborators or colleagues at MSKCC, Stanford, Rutgers, and elsewhere. And thank you for your attention. Any questions? Yes?
How would your modeling fit in with the actual robot experiment?
So it's going to depend on exactly what experiment we're doing. But so the binding experiment is going to be, basically we're going to be doing high throughput binding experiments on the robot. Basically similar to the model of, or the video of the ligand wiggling and binding the protein. We calculate the binding affinity and then we compare that to experiment. And my lab mate Sonia there is actually the one doing those experiments. So the idea is to really automate and really make it high throughput and hopefully not painful to do. So.
On your robot, who's creating the buffers? You get water as a buffer. Who's creating the other buffers?
Well, we actually have a buffer maker that we are. So we could do two things. We could actually, the robot itself has a liquid handler on it. And we also have another robotic buffer maker. What's it called? It's called a Revo. It's from a startup in Boston, LabMinds. And it's like a giant, it looks like a giant vacuum cleaner or something. It's like as big as a refrigerator. And it just makes buffer in an automated way. And they have like a pretty cool iPhone app, and it's all web-based and on the cloud.
I tried running folding at home, but every time it completely takes over my machine.
Yeah, it really wants to use all your flops. It wants, particularly if you have a GPU, it will definitely eat up the GPU and as many cores as.
It's even noisy to leave it at night, right?
Right. Yeah.
I tried it, but
Yeah. All right. Well, thank you.